Good afternoon. This session in some sense is a natural continuation of benchmarks and evals because mathematics is a natural way to benchmark AI systems. So AI has been progressing through different levels of complexity that I outlined here, different levels of difficulty of math problems, going from elementary school to middle school, then to high school, graduating into college. That's actually where AI systems roughly are right now at the level of consistent performance. Keyword here is consistent so that they can solve problems really reliably with high fidelity. And then as a professional mathematician, to me, this hierarchy goes on and on. In fact, there are graduate level problems which we give on various hard exams. Then there are graduate level problems that we assign to students. And if they solve it, they actually earn PhD thesis. And then the hierarchy continues into professional math research. There are several levels there, including problems which we as research mathematicians have no idea how to solve. There is gradation there as well, which includes perhaps Millennium Prize problems at its highest level. And this talk is about a question whether AI systems can reliably reach that highest level of performance. In other words, you can think about this talk as, can we get artificial superintelligence? It hasn't come yet, but the question is how far and what are the bottlenecks? So it's easy to benchmark. As I said, this talk is in a way benchmarking talk because there are lots and lots of math problems. For example, website over there lists for you about 100 unsolved hard math problems, which do include all the Millennium Prize problems, but there are plenty of others. Among these problems, there is a very simple one, which I myself didn't know about, but surprisingly, it's easy to state, but hard math problems that belongs to that list. It's like, what is the longest snake you can fit on a hypercube? So imagine a cube of size 2 by 2 by 2 and some number of times up to dimension. And so in other words, each side is length 2. So question is, what is the longest snake you can fit in such cube in d dimensions? So when I heard about this problem about half a year ago, I thought that for large D, we can probably make progress with AI because for small values of D, mathematicians and computer scientists probably have figured it out. So it turns out that the system we built managed to beat the record, which for a long time has been standing even in dimension 9. And this is an easy-to-state problem, but it has connections to cryptography, quantum computation, and other domains. So what I like about math and benchmarking on math is that you can try on this problem, for example, with any system you want. So for example, you can throw Fable at it or AlphaEvolve and see how it does. Of course, we have tried and nothing happens. I mean, it just doesn't solve it. So what are the bottlenecks? Let's look at another problem. So this is another one we tried recently, and this problem came from a professor here in Berkeley, David Eisenbud, who suggested this problem as a really hard problem on commutative algebra. And we managed to solve it, and I'll tell you a little bit about the journey by the end of the talk, how it went. But here the problem is to look for some esoteric concepts in commutative algebra, monomial ideals with two properties. And it's easy to find monomial ideals with one of the two properties individually, but once you combine them, you're looking for a needle in a haystack. So that's where probability drops to 0 in this distribution plot. So we struggled a little bit and designed several, in fact, many systems through all kinds of AI systems at it. It was very clear that it has hierarchical structure, this problem, that there are two steps and they should be outsourced to two different individual components of AI system. But then even once you know that you want to approach it with some version of other multi-agent system or HRL, it still requires a lot of iteration to find the right one which works. So here we had to design architecture which is ideally suited for this problem and lots of other things. So the third problem I'm going to give in this talk as an example is from yet another area of mathematics. This is from group theory. The problem is called Andrews-Carrier conjecture, and that's another problem that's been open for 60 years. So here, the problem is very much like Rubik's Cube. In fact, many problems in group theory are kind of like Rubik's Cube. So you're given some state, and the goal of the agent is to find a path to the goal state. Goal state for the Rubik's Cube is where all faces are colored in the same color. So this is kind of a glorified version of that. Except that in this case, the search graph is not explicitly presented, and the problem itself is asking, can any state reach the goal state? So that would be the CS formulation of this problem. So again, we managed to make progress on it, and all of our papers are published in ICML, ICLR, and Europe's. Even though they make progress on math, we have to design AI systems with lots of interesting bells and whistles and insights. For example, in this case, one of the insights was the data distribution on the problem, that in Rubik's Cube, it's easy to scramble and generate data on which you would be training it. But here in this problem, what happens is that this distribution of the data is very bimodal. In other words, scrambling and just random search and so on gives you very primitive data which is in the vicinity of the goal state. But there are some states here which are super exponentially far from the goal state. And the question is, how do you train RL to reach those, kind of the other hump in this data distribution? So these are kind of problems that we work on, and now I can do a proper introduction. So I lead a lab at Caltech, which is laser focused on solving math problems, but really what we're really focused on is building AI systems, AI tools for long horizon and sparse reward problems. Because if you ask what's in common in the problems I just mentioned, and that's actually going to be the feature of any really hard mathematical problem, is that your system will have to reason for many, many steps, and even if you have very high fidelity, it can fail over 100 steps, but 100,000 and 100 billion steps, that's actually what we need for these problems. That's where you need not just 30% improvement, but really many, many X% improvement. So these two issues, long horizons and sparse rewards, each are challenging, but when combined, they just become notorious bottleneck for all these math problems. So it's good to look at other domains where either long horizon or sparse reward tasks occur, and there are quite a few. So it starts actually with Atari games, and I'll come back if I have time to games and AI for games. Of course, coding, robotics, autonomous transportation, all these tasks require either long horizon or sparse reward or both combined. There are some things that we know how to do, so various exploration, curiosity modules. They help to generate, turn a sparse reward problem into a more dense signal that we can explore gradually and generate sub-goals and subtasks to solve the main problem. More recently, learning world models, of course, is very helpful, but again, it gives a few X or 10X improvement, not billions of X. So that's what we really need. There are all kinds of bells and whistles, such as harnesses, that everybody and us are trying to use in various ways. But again, so far, none of the Millennium Prize problems has been solved. So the problem is still open. And there are quite a few challenges out there where we're debating whether LLMs is the right underlying framework. For example, can they reason, or are they just good at retrieval? So that kind of generalization question is one of the vexing questions here. Another is, I already alluded to it, is RL an integral part, which makes things more robust, helps to improve performance either in post-training, alignment in various stages, but is it really enough? We don't know yet. So again, for this superhuman reasoning, that's going to be the question. If you look at SWE bench, then yes, coding agents are pretty good now. Performance usually ranges in 70, 80 percentile. But if you ask what are the bottlenecks in this remaining 20%, it's exactly this long horizon tasks, where if agent has to fix some bugs in the code spread over several Git repos, find different files, then it gets lost. In particular, because over this long horizon, it knows that there are several components, but detecting where exactly the bug is or what exactly has failed, that becomes a challenge. I mentioned that In terms of computer games, that's also a good comparison. So going back to DeepMind's DQN algorithm, which was introduced in 2013, it failed miserably on this game called Montezuma Revenge, which then became an obsession for AI or reinforcement learning community, trying to design the right algorithm which would actually do well on this game. And this became almost like a decade-long journey. So many teams tried and many teams failed, until finally, by 2018 or 2019, we got some good signal, and now, of course, the problem solved. I want to point out that this period of exploration did include 2015 to 2018, when we had AlphaGo, AlphaZero, and MuZero, and none of those models actually performed well on this particular game because it was a good example of a sparse reward problem. So this is a good illustration of how it looks like to design AI system for math. You also try lots of different things, and pretty much all of them fail, especially if your problem is really hard, this long horizon sparse reward problem. So our cycle in our lab is very much the same research cycle as in any other AI lab. We design AI, we deploy it, we look at the W and B curves, we see what the signal is, most importantly, why it failed. So we try to analyze why it failed, and then we try to implement it in a new cycle, and so on and so forth. So this, in principle, can be fully automated. And I want to point out that currently we can't. For example, we can't do it with AlphaEvolve or other tools, simply because this version of algorithm development, algorithm design, discovery, is by itself a sparse reward problem. So unlike coding, where agents are pretty good, current agents are not so good at discovering really new algorithms way outside of the box. And bottlenecks typically have to do with evaluation, because your system is going to be just as good as evaluator. So in practice, what happens is that your evaluator sets up certain guardrails, criteria, conditions, and the agent quickly learns to hack it, simply because the original problem that you're trying to pose is just way too hard, and it's much easier to do hacking into one or the other type of behaviors. For instance, going back to OpenAI, this Coast Runner bot, which learned just to zoom over, collect some mediocre rewards instead of finishing the race. That happens in math problems as well. DeepMind had this Lego stacking challenge, where the robotic arm quickly learned that it's easier to trick the camera just to flipping the Lego blocks upside down so that the height appears to increase a little bit, and collect rewards in that way. And there is also, of course, reward tempering. For example, the Palisade research example, which is the last illustration with chess, where AI system managed to learn how to remove the opponent's engine completely in order to win the game. So this happens in all of the math problems, especially hard ones, once you try to throw AI at it and you encounter same type of challenges. So the title of my talk is The Future of Math AI and Sparse Reward and Long Horizon Tasks. I'm actually very excited that we are at this point where for really hard math problems, to solve them not one by one, like I showed you in the beginning, but in mass production. So we can actually have superintelligence that can reliably solve pretty much any problem that I cannot solve as a working mathematician. So for this, we need to unlock this sparse reward and long horizon capabilities. There are many open questions. We're in a very good point right now, very sweet spot, where a lot of work has been done, but we're definitely far from solving this in the future. Just like in the past years, everybody would say that data is all the key, basically. You need clean data. Data is everything, right? So now, as we're exhausting data and entering the new era, I would say that for this new generation of AI systems, various tools and harnesses is going to be the new action space. And what replaces data stack is now reward stack. So setting right systems, like channeling the agent to go in the right direction, is exactly what we need for this long horizon task for sub-goal decomposition, which is reliable and so on. Of course, there are many other engineering challenges, such as it would be good to have this multiple agents work in teams for days and months. and that requires different AI agents to talk to each other, very much like we have with internet protocols in early days of World Wide Web and so on. And finally, I want to conclude with, I'm optimistic, I'm excited, otherwise I wouldn't be standing here and talking to you about it. So a week ago at International Congress of Mathematicians, 4 Fields Medals were awarded. So International Congress happens once every 4 years, kind of like World Cup, Soccer Cup. So I hope that 4 years from now, we'll see Fields Medal awarded to AI plus humanity. Thank you.